This is the S-500 Prometey, mobile Russian air and missile defense system built to do something that sounds almost unreal. Search the sky, sort through chaos, and attempt to strike targets not just high above the battlefield, but near the edge of space itself. Open source reporting describes detection ranges stretching hundreds of kilometers, with some claims pushing ballistic target detection out to around 2,000 kilometers. That means this system is not simply watching the horizon. It is watching layers of the atmosphere that most air defenses were never meant to dominate. But how does a convoy of radar trucks, command vehicles, and launchers actually hunt something moving at several kilometers per second? And what makes the S-500 different from the systems that came before it? To understand that, we have to look past the launch tubes and into the invisible architecture of detection. Classification, tracking, and interception. At first glance, the S-500 looks like another member of Russia's long-running family of surface-to-air missile systems. Big trucks, big radars, big missiles. But that first impression is misleading. The real story is not just size. It is specialization. The S-400 is largely known as a very long-range air defense system. The S-500 was presented as something more ambitious, a system meant to bridge the gap between traditional air defense and strategic missile defense. In other words, it was built for the moment when ordinary targets stop behaving like ordinary aircraft. That distinction matters because the hardest targets in the sky are not the ones that are merely far away. They are the ones that are incredibly fast, extremely high, and visible for only a short and unforgiving window of time. A cruise missile may weave low. A combat aircraft may maneuver unpredictably. But a ballistic target creates an entirely different engineering problem. Its speed can be immense. Its trajectory can cross enormous distances. And once it begins descending, every second disappears with brutal speed. An air defense network that can handle aircraft is not automatically a network that can handle that. That is one reason the S-500 exists. It emerged from a problem engineers had been confronting for years. How do you create a mobile system that can move with military formations or protect major regions, while still engaging targets that belong to the world of missile defense rather than ordinary anti-air warfare? Fixed strategic missile defense sites can be powerful, but they are not flexible. Traditional mobile air defenses are flexible, but they may not reach high enough or react fast enough for the most demanding threats. The S-500 was presented as an attempt to combine mobility with a far more ambitious engagement envelope, and that immediately creates a fascinating contradiction. Mobility usually means compromise. A mobile system must fit on roads, on heavy chassis, and deployable units. But missile defense usually demands immense radar power, precision tracking, high-speed computation, interceptors capable of climbing 2 extraordinary altitudes. Putting those worlds together is like trying to build a portable observatory that can also function as a split-second defensive machine. However, that is exactly where the S-500 becomes interesting. What people often call the S-500 is not one vehicle. It is really a moving ecosystem. Open source descriptions list launcher vehicles, command posts, acquisition radars, and separate engagement radars mounted on different heavy trucks. Some are built on 10x10 chassis, others on 8x8 or 6x6 platforms. So when you imagine the S-500, do not picture a single launcher waiting for orders. Picture a convoy that unfolds into a sensor and shooter network. In practical terms, it is closer to a mobile air defense laboratory than a single weapon. That distributed layout is part of the system's power. One radar can search, another can refine. Command posts can fuse the data. Then a launcher can fire the specific interceptor best suited to the target. It is a bit like a team of specialists in an operating room. One machine monitors, one measures, one guides the procedure, one delivers the decisive action. The S-500's hunting ability comes from that cooperation. Open source assessments commonly describe 4 major radar-related elements in an S-500 battery. There is a long-range acquisition radar for broad area search, another acquisition radar working in a different band, a multi-mode engagement radar, and a dedicated anti-ballistic missile engagement radar that tells you something important immediately. Engineers did not trust one radar to solve every problem. They separated the task. One layer looks far, another sharpens the picture, another focuses on the exact geometry of interception. For the most difficult class of targets, there is a radar specifically tied to the anti-ballistic mission. Why does that matter? Because hunting a target is not the same as merely seeing it. Detection is just the first step. A radar return might be an aircraft, a missile, debris, or something meant to confuse the system. The S-500's job is to do far more than notice a distant object. It must decide what that object is, how fast it is moving, where it is going, whether it is dangerous, and which interceptor should be assigned to it. And it must do that before the target passes beyond the best point of engagement. That is where the S-500 begins to resemble a giant predictive engine. It does not simply react to where a target is, it reacts to where the target will be. For slower threats, that is challenging. For ballistic threats, it is everything. If an incoming object is moving at extreme speed, firing at its current position would be almost meaningless. The interceptor must be sent toward a future point in space, not a present one. The radar therefore feeds the command system not just a location, but a constantly updated forecast. And this is where the system's architecture reveals its deeper logic. Open source sources describe the S-500 as using different missile types for different jobs. The 40N6M is associated with long-range air defense engagements against aircraft and cruise missiles. The 77N6 and 77N6N1 are associated with the anti-ballistic role, including very high-altitude targets and, according to various reports, even low-orbit satellite targets. That split is critical. The system is not relying on one universal missile to do everything. Engineers divided the mission into categories, then paired each category with a more appropriate interceptor. That may sound obvious, but it solves a major engineering problem. An aircraft interceptor and a ballistic missile interceptor live in different worlds. One may need agility, endurance, and the ability to engage maneuvering aerodynamic targets. The other may need blistering climb performance, extreme closing speed, and guidance designed for a target that may spend part of the engagement in near-space conditions. Building separate missile families allows the system to avoid forcing one design to carry every burden. And the performance claims surrounding those interceptors are exactly why the S-500 attracts so much attention. Open source reporting commonly places the 40N6M around a 400-kilometer range, while the 77N6 family is often reported in the 500 to 600-kilometer class. Claimed engagement altitudes for the S-500 reach roughly 180 to 200 kilometers for certain target types. To put that into perspective, commercial airliners usually cruise around 10 to 12 kilometers above Earth. Even high-performance military aircraft operate far below that upper envelope. The S-500's most dramatic claims are not about defending ordinary airspace. They are about reaching into a layer where the atmosphere becomes thin. Flight behaves differently, and the line between air defense and space tracking begins to blur. But that is only part of the story. Range numbers on paper do not automatically create a successful interception. The true secret lies in timing. The S-500 hunts targets by compressing an enormous chain of events into a very short decision cycle. First, the search radar scans a vast volume of space. It is not looking for one neat object against a clean background. It is sorting through clutter, altitude differences, signal reflections, and multiple target types. Once something important appears, the system begins establishing a track. That means repeated radar returns are compared to build a stable estimate of speed, heading, and altitude. Next, the command post takes over the logic of the fight. It fuses data from multiple radars, decides whether the object is an aircraft, cruise missile, or ballistic target, and determines which engagement path makes sense. This part is essential because the wrong decision wastes the most valuable resource in air defense: time. A long-range ballistic target descending at enormous speed does not offer the luxury of hesitation. Then the engagement radar locks into a finer, more precise role. Think of the acquisition radar as the system's wide-angle vision and the engagement radar as its precision instrument. The goal is no longer merely to know that something is out there. The goal is to create a fire control quality track accurate enough to guide a missile into a narrow collision geometry. Only after that does the launcher become the center of the drama. The selected interceptor fires vertically from its tube, rises hard, and receives guidance updates as it accelerates toward an intercept basket in the sky. At this stage, the missile is not simply chasing. It is being managed as part of a moving geometry problem. The target moves. The missile moves. Earth curves below them. Time to intercept shrinks. Radar updates continue feeding corrections. The entire engagement becomes a race between prediction and reality. For aerodynamic targets such as aircraft or cruise missiles, the process is already demanding. For ballistic targets, it becomes extraordinary. These objects may be approaching on steep paths and at velocities that dramatically reduce reaction time. That is why open-source analysis pays special attention to the 77N6 family and the claim that these interceptors may use a kinetic hit-to-kill approach against ballistic targets. In simple terms, instead of relying primarily on blast and fragments, the interceptor attempts to destroy the target through the sheer energy of collision. At first, that sounds almost impossible. Hitting a fast-moving object with another fast-moving object in the upper atmosphere is not just difficult. It is one of the hardest guidance problems in modern defense engineering. But engineers solve this problem in a remarkable way, at least in concept, by turning the engagement into a chain of increasingly refined corrections. Long-range radar finds the target. Tracking radars reduce uncertainty. Command systems predict the intercept point. The missile climbs into the right corridor. And in the terminal phase, the final guidance must collapse the remaining error to almost nothing. That last phase is where all the earlier precision pays off. If the track quality was poor, the missile arrives in the wrong piece of sky. If the timing was late, the window closes. If the target classification was wrong, the wrong interceptor was launched. The entire hunt depends on every earlier layer doing its job. That is why the radars may be the most important part of the S-500 story. Launchers are visible. Missiles are dramatic. But radars are where the system actually begins to think. Open-source descriptions suggest airborne target detection out to roughly 800 kilometers and ballistic target detection at much greater distances, sometimes reported up to around 2,000 kilometers. Whether those figures are achieved under real conditions is a separate question. But the design philosophy is unmistakable. The S-500 is built around seeing farther and earlier, so that the rest of the network has enough time to act. And that leads to the most impressive engineering feature of all. The S-500 is not just an interceptor battery. It is an attempt to create a mobile, layered, target-discriminating shield that can treat very different objects in very different ways. Aircraft, cruise missiles, ballistic missiles, and possibly certain low-orbit targets do not look the same, move the same, or need to be engaged the same way. Yet the S-500's architecture is designed to place them inside one integrated decision space. That is a profound systems engineering challenge. However, the real-world picture is more complicated than promotional claims. Open-source analysis also points to delays gradual production and lingering uncertainty about some of the most dramatic advertised capabilities, especially against hypersonic threats, that caution matters. Advanced defense systems often exist in three versions at once: the version described in official statements, the version proven in testing, and the version fielded in meaningful numbers. Those are not always the same. So the S-500 is important not only because of what it is claimed to do, but because it shows where missile defense technology is trying to go. Operationally, the S-500 appears intended to sit above systems like the S-400 rather than simply replace them. The S-400 remains primarily associated with air defense duties against aircraft, cruise missiles, and some ballistic threats. The S-500 is presented as a higher-tier layer. It's meant to complement existing defenses and add stronger capability against faster, higher, and more strategically important targets. In that sense, it is not a bigger version of the same idea. It is a different layer in the defensive pyramid. That layered role helps explain why countries invest so heavily in systems like this. The value is not just in destroying a target. It is in changing the calculations of anyone planning to launch one. A defense network that can see farther, track higher, and react faster forces an adversary to devote more effort to speed, stealth, decoys, maneuver, or saturation. In other words, systems like the S-500 shape strategy even when they are not firing. And yet perhaps the most fascinating thing about the S-500 is how it changes our picture of what an air defense system is. Older generations were often thought of as shields against aircraft. S-500 belongs to a different category altogether. It treats the sky as layered battle space, from low-level threats to near-space trajectories. It suggests a future where the boundary between anti-air warfare, missile defense, and even limited counter-space capability becomes increasingly blurred. That is why the S-500 matters beyond any single headline number. It represents the evolution of defensive engineering from point protection toward predictive, networked, multi-layer interception. Its real weapon is not only the missile. It is the chain, radar to command post to engagement radar to interceptor, interceptor to collision point. A hunt measured not in footsteps, but in data, speed, and fractions of a second. And when you look at it that way, the S-500 becomes far more than a group of trucks carrying missiles. It becomes a machine built to solve one of the most difficult problems in modern engineering: how to find, understand, and meet an object moving at extraordinary speed in a sky that is no longer just sky. That is what makes it so compelling. It's not because it is large, though it is. It's not because it is secretive, though much about it remains uncertain. But because it reveals how far military engineering has pushed the science of sensing, predicting, and intercepting motion itself. And that is also why systems like the S-500 continue to capture so much attention. They are not just weapons platforms. They are demonstrations of what happens when radar physics, vehicle engineering, guidance theory, software, and strategic necessity are all forced into one moving architecture. If you enjoyed this deep dive into one of the world's most fascinating defense systems, subscribe for more explorations into remarkable machines, aerospace technologies, military innovations, and scientific breakthroughs that redefine what engineering can do.